So hi everyone. James, you coming in? So obviously the other day I was having some struggles, and I just really what happened is I got lost somewhere in here. So a couple of solutions. First of all, Jim sent this to me, which I believe is this what we tried?
I think you had the right answer. It was just that there's a trick where, and you alluded to it, where you separate the equations to get the 1 plus, and
Yeah.
I think you didn't see it. I cheated because I looked at the first edition of the book, and the previous equation to the final solution is what got me where I got the answer.
If you guys want to take
changed
a look.
Oh, there we go. Jesus.
You pulled out the E, or the epsilon. I keep saying E, but epsilon. And then 1 plus W, and then you changed it to epsilon plus W, and I think that might have been something that was important to have in there.
Yeah.
As opposed to W plus epsilon, which would have given you some other term. But what it did is I made the mistake originally with the minus sign, I think, and then that just got all messed up.
Yeah.
So this is this is kind of a lesson that I learned in this class a long time ago. The very first time I taught intermediate, I spent hours and hours and hours working through problems. And I was like, there was one problem I did. I spent 18 hours, talked to a physicist from Czechoslovakia at the time. And it was ridiculous. I couldn't figure it out. Well, what I realized is that there was an error in what I was assuming. Actually, I don't think it was an error. I think it's an error in the problem. And once I assumed something set to 0, the whole thing fell apart. But there was a lot of times I'd run into problems. And so what I started to realize is that I can do this. I have not done it, but I can do it. There's nothing in here that I cannot do. So sometimes it takes a little bit of time to get to go through it. So this was Jim's solution, and then I gave you my solution, which was, where is it? Okay, so let's just kind of take a look at the solution that I had. Is the problem is I've got this 1 over epsilon thing in here.
You want to share your screen?
Oh, yes. Wait a second. I didn't share my screen that whole time when I was showing your solution?
Correct.
Where's the share? Nothing like forgetting to share screen. Okay, once again, then here's Jim's solution. You all can see this now, right?
Mm-hmm. Yeah, there's one error in that, and it shouldn't be an equal sign. It should not be an equal sign. It should be approximately equal.
Right. Oh, down here approximately, because you're losing the higher order terms.
Exactly.
So, well, whatever. So that's fine. So that was good. And then I said, okay, well, here's what I ended up doing is I just took this fraction and I broke it up into 2 parts, right? So, and this, I'm telling you, I know students. Life with students is always interesting and entertaining because students will do amazingly dumb things. So let me show you something that you cannot do. Okay, and I'll just make it quite simple with something like this. Oh, it helps if I don't draw white on white. If I do.
Your pen ran out of ink.
There we go. The ink wasn't working for someone. What is going on? Pen mode. There we go. Okay. So there's on this device, there's a little click, these little buttons, and that's right where you hold the pen, and I'm like, what? Okay, so A plus B all over C plus D. You cannot do A plus B over C plus A plus B over D.
That's a different critter.
That's bad, okay? You can do A over C plus D plus B over C plus D.
Yes.
You can always do the common denominator, separate that out. And I know this is kind of stupid, but when you start doing more and more problems, you've got to be aware that you can do things like this. So what I'm going to do is I'm going to take this out. And what I did is I took it over, and really what I need to do is have this parentheses in here, but I said W plus epsilon all over 1 plus W. Okay, so when I did that, I have W over E over 1 plus W plus epsilon over epsilon, because that's what I have in the bottom, 1 plus W, you see? But I didn't have to do that because these things were going to cancel out. So what you're left with are two simple things. So 1 over 1 plus a number is commonly used. And so what you end up getting, and this is where you start getting the series and sequences, and I don't know if you've ever done Taylor series and stuff, but you're going to get 1 minus W plus W squared minus W to the third, and etc. You're going to have this sequence. It's called an alternating sequence, and we just keep going to one higher power. So by doing this synthetic division that you get here, it's very quickly that you start getting into the square terms. And we said we're squaring something that's already in 1,000th of a decimal point, maybe 100th of a decimal point. So now we're looking at something that would be 4 degrees, 0.0001, and then that's the difference, the 0.0001. So once we get to a square term, we get rid of that and anything else higher order terms. We just get rid of those. So I know that 1 plus 1 over W, because is approximately equal to 1 minus W. So because I wanted you to see how things work, let's try one. 1 plus 2, we know is 1/3, right? We know that. Is that equal to 1 minus 2? And the answer is no.
No.
Because we said this only works when W is small. So let's get rid of that. Let's try 1 over 1 plus 0.01. Now on your calculator, go ahead and tell me what the answer is to 1.01. 1 divided by 1.01.
0.99.
It's got to be something close to 1.
How far does that go? 0.99?
0099009900. So
Okay, so it keeps,
whatever the repetitive
keeps
symbol.
going on over there. So if you wanted to say 0.9901, that would be whatever, right? So is that approximately to 1 minus 0.01, which comes out to be 0.999, right?
Mm-hmm.
So now we're only off by a very small number. So when this number in the denominator gets really small, you start to see, well, that's really close. And we're going to see tricks like that within this book. I'm not going to do it now, but we're going to start to see tricks like that. So that just remembers, the whole reason we're able to do this simply is because this is a small number. That's where the small number is. Because mixing ratio is supposed to be in kilograms per kilogram, but we say it's in grams per kilogram. So even at the high end in the tropics of 20, that's still 0.02. So really hot temperatures, your virtual temperature correction is a little bit more inaccurate, but not by very much. We only measure temperatures to within the nearest 10th of a degree, maybe 100th of a degree anyway, so we're not going to worry about things too much. Anyway, that's this side. That's where the arrow is. When I go to the other term, all I'm really looking at is this term. This time instead of 1, we have 1 plus W. We have W over 1 plus W. So now we have to do the synthetic division, and because it's a lot simpler, it works out a whole lot better. So I moved down a little bit, and I hope that you saw very rapidly, 1 goes into there, W times, you start subtracting, and now we still get, again, we get another alternating sequence, but rather than starting with 1 plus that, we get W minus W squared, etc. So when I put this back, oh shoot, sorry. When I put this back into the equation, I have to have both terms. Remember, I have a 1 over epsilon. This came out, so what I said is W over 1 plus W is approximately equal to W when W is really small. Which, again, I hope you can see that I don't have to actually do problems to see that one. But I have a 1 over epsilon. So this becomes W over epsilon plus the other side, which was 1 minus W. Once I have that, now I'm ready to solve it. And I'm like, this is all multiplied by the temperature. And I just took the term. So I multiplied through by temperature. And I get temperature times W over epsilon plus temperature minus temperature times, just keep in mind this is not the wet bulb temperature, temperature times W. Because I have this in there, right? Whoops. Because I have the temperature, I brought it to the other side. So what I'm saying is I'm looking for what's the difference between the actual temperature and the virtual temperature. It's what we call the correction.
Correction, yeah.
And then when I take the remainder terms, I take T, and then I take from this term and this term, I take the W out. So it's T times W. I have 1 over epsilon minus 1. But again, common denominator, this is epsilon over epsilon. And then I've got 1 minus epsilon. And that's the equation that's in the book. Now, epsilon is a number, right? It's the ratio of the ideal gas constants. And that becomes 0.622. You plug it in, and then with all that said and done, let's go, what page was this on?
68?
68?
No, I lied, 80.
Oh yeah, because we skipped quite a bit ahead. And we get a very simple expression of this. That whoa, that's a really big
Perfect pencil.
TW is equal to T times 1 plus 0.61 W. So what I'm going to do is I'm going to say, what is the, oops.
You mean TV?
Yeah, TV. What is the virtual temperature when the temperature is 32 degrees Celsius and the dew point is 21 degrees Celsius? So go ahead and how would you solve that? What do you need in order to solve that? What would you need to do to solve it?
You'd need W.
Convert to Kelvin.
Okay, well, you need to convert to Kelvin. And what else do you need?
W.
How do you find W? What do you need to get?
Oh, the mass of water vapor and the
Yep,
mass of
no.
dry air. Oh, the mixing ratio.
Right? You don't know what the mixing ratio is if I give you the dew point. So you have to find a way to convert it. Now there's charts, I think, but if you use the thermodynamic diagram, you can get an answer. And what else would you need to know? There's one other thing. If you're using a thermodynamic diagram, what else would you need to have?
Temperature.
You got temperature.
Yeah, temperature.
Oh.
You need something else. Jacob, what do you need?
That is an excellent question.
Well, then try to do it. Go get a thermodynamic diagram. Go online. You know where they are. And find this. Allison, you remember where they are? Just go to our homepage, and if you go to academics under severe weather, it says thermodynamics. So you can use that diagram.
Oh, oh, I'm sorry. I didn't know what you were asking for. Yeah, the thermodynamics diagram. Yeah, I know where those are.
So, and once you start there, you're going to find the dew point. You're going to tell me what W is equal to, and then you're going to ask me what else I need.
TV is always greater than the environmental temperature?
Yes.
Okay.
Because this is always a positive number.
Right.
Does it say I'm recording right now? Is it recording?
Yes.
Started again?
Yeah, I got the warning when I joined in.
Did you see it pause?
I didn't see it pause, but
Here. And now you see it recording.
Yes.
Okay. See, what happens is I don't have that notification on my screen when I share.
okay.
So what else do you guys need to know? James, wake up.
I'm here.
Do you drink coffee, James?
No, I got a soda, but that's about it.
Maybe you need coffee. If you're going to be a true meteorologist, I believe you need to have coffee in the morning.
Like some sort of ritualistic.
Oh, it was my
ritualistic
birthday
requirement.
yesterday.
Happy birthday, Allison.
Happy birthday.
Happy birthday.
Happy birthday.
Happy birthday.
Come on, guys. What else do you need to know?
I don't know. I forget how to do this. It's been a minute.
Pressure? The altitude it's at?
Let's say that. If you don't know the pressure, how are you supposed to know? You always, remember, for any thermodynamic diagram information, you always need temperature, dew point, and pressure. Bob's going to give you all these things. You got to have it. And Bob's from Texas. Bobby's barbecue.
Good old Bob.
Someday in heaven, I'll tell Bob about how famous he became.
Can you do a quick summary of what Bob is so I can explain it to Emily?
Bob, when I went to Dallas, Fort Worth, I was videotaping and taking pictures of a Radiothon launch. And the guy who was doing it, his name's Bob. And he was a really nice guy. He had a big Texas belt on and a styrofoamy type hat. And so when you looked at him, you're like, Bob is definitely from Texas. So his name actually was Bob. He was actually from Texas in Dallas, Fort Worth. And so every time I show pictures of that balloon launch, we talk about Bob. And it becomes, how do I know what the atmosphere is doing? Ask Bob. Because Bob is the one. And Bob always has to give you those three things.
Yeah, we're doing the hypsometric equation right now in dynamics, and I said the thicker the warmer, the thinner the colder. And he's like, yep. I'm like, okay, write it on the board, because the way I explained it is confusing.
You know, that's good, because we're going to be doing the hypsometric equation.
Last thing.
Right now. So everybody, what, did you get an answer yet?
No. I forget how to do this.
Bruce, you got it? Well, did you find what W is?
I couldn't find it. My thermodynamic diagram is in.
Here, that's what I'm saying. So if you're over here, let me just hide this and stuff. right? If we're over here, all you're doing is going to the home page, and anytime we go into academics, right, class notes, severe and unusual, you can always find a good thermodynamic diagram. So you always have access to this. And I take all the lines, and then you've got a nice one. So now I'm here.
It's in centigrade degrees, and I presume we're in Fahrenheit, but
No, we're in centigrade.
You're in centigrade, but you have to go to kelvins. Okay, so I'm going to have to erase this whole thing, which is fine. So here we go. I'm at 20 degrees at 950 millibars. So I put a dot there.
Okay.
And I'm looking at the value of the line. So here's a mixing ratio. Oops. Right again. Here's a mixing ratio line that's valued at 15. Here's one that's valued at 20. And I'm looking for one that would be valued through that point, which would be, I don't know what, 21 and a half maybe? Are you guys following that?
The mixing ratio?
No, you mean 16 for a mixing ratio.
Yeah.
16 or 16 and a half?
Yeah.
Yeah, sorry.
Yeah, I see that now. I was getting.
Okay, so W, let's just say W is 16 grams per kilogram. All right, so we take the temperature, virtual temperature, is equal to the temperature. And what did we say the temperature was?
Didn't you say it was
32.
32. Well, but I'm going to convert it to Kelvin.
305.
So I add 273. I get 305 K times 1 plus, what'd you put in there?
16?
No, 0.61
621.
Oh, yeah.
times 16. Is that what you did? Plug those numbers in and tell me what you get then for the virtual temperature.
Yeah, the kids here, they don't even do the thermodynamic diagram.
Yeah.
I asked them, I said, so did you guys do this? They're like, we've seen it, but we
We've
never
seen it.
did it. I'm like, you've never done this by hand?
No.
I'm like, what do you mean?
That's why you're a great student, Allison.
That's why all my transfers, all my credits transferred. I came in and I only had to do 300 and up classes.
That's awesome. Did you guys get the answer?
315.76.
315.7.
Yeah.
Is that what you all got? James, what'd you get?
I'm trying to read that. It's
Write it down. James, wake up, man. You are like falling asleep. Did you sleep last night?
yeah, surprisingly. I'm just had a, hold on. I totally should have done this.
This is the formula that you should have written down. I've been going through it. It's in the book. Nick, what'd you get? Did you get 315.7?
That should probably help.
Jacob, what'd you get?
Not that.
What'd you get then?
I'm still trying to read what you wrote down.
Guys, look, right there. Page 80, equation 3.60.
I have a question.
It's in there. It's like this. This is the equation, but I'm just doing. That's the equation. That's what we're using. All you need is W.
Are we using W in, is it 0.16?
Oh, you gotta be kidding me. Why is she
No, I got the wrong answer.
up?
Because I'm getting some number that's not 315. So
What
I'm
did
trying
you get then?
to got like 3,000 something. So I know it's not right.
Yeah, you did something wrong. Hold on. Hold that thought. How about the rest of you? Nick, what'd you get? Did you get this answer?
No, I'm getting the
Oh.
3,000 as well. I think it's because do you plug in 16 for the mixing ratio, or is it 0.16?
Yeah.
Okay, well, that's your problem. W is in grams per kilogram.
It's 307. It's 308.
It's got to be kilograms per kilogram. That is, remember, kilogram per kilogram is unitless.
Right.
And actually, I don't know if they say unitless or they say dimensionless or non-dimensional. I think that's the word that scientists often use. Same thing, right? No units.
Okay, I get 307.9, so it's
Well,
308.
Because you're taking 16, you have to divide it by how much?
1,000.
1,000.
1,000 is 0.016.
Yeah, I get 308 now. Now that I
Yeah,
do-
that's what I
Yep.
get. Or 35 degrees centigrade.
308.
Yep.
Now you're at a much better answer.
Yeah.
Okay?
3,000 seemed a little steep.
Grams per kilogram.
So now, boys and girls, if we do this, and we go to analysis, and I go to upper air soundings, and I pick up a sounding, let's say in South Carolina, and I look at this, not that one, but I look at maybe the sharp high sounding, and whoops, where did it go? Oh, I can't zoom in when I do this. Shoot. Or maybe I can. I just have to re-hit it. So over here, if you, I know it's a little bit hard to see, but there's your temperature. There's your temperature. And there's your virtual temperature correction. And given the fact that we're around 1,000 millibars with W very high, up in the 20 plus, that's a couple of degrees.
A couple of?
Correction is pretty high.
A couple of degrees?
A couple degrees.
You said a couple of degrees.
Couple of. If I say couple of, then that's abbreviation for of.
I thought you said we can't do that.
You can say couple of, but you can't say couple degrees.
Okay.
You could say
Like there's a couple hurricanes?
there's a few hurricanes. That's what you do. Okay, so does that make sense to you with the virtual temperature correction?
No, it's because he doesn't like
I know he doesn't like the shovel tornado.
No, he
So
loves-
that's what these soundings are all about. I'm not happy with the way that we do them here. I think they're confusing,
I agree.
but I don't know another way to do it. I haven't figured that out. Okay, so that's what we're doing. Does that make sense now? Oops.
I think so. Can we go see the equation one more time just so I can
Page 80, get your book out.
I meant the finished one.
308 is equal to 305 paren 1 plus 0.61 times 16 over 1,000.
Paul, what page am I going to?
Time is it?
Thank you.
31.
And if you do this right, this is what it's going to be, James. You've got to get kilograms per kilogram, which is 0.016. And I was hoping that a lot of you put 16 in there, and then you're getting the wrong number.
Yeah.
Okay, and then Allison, you said, do I use 0.16? No, it's 0.016. Then all it is plugging that in, and that's where you get 308. So that's a sizable contribution. The air is considerably less dense because of that amount of water vapor in there. 16 grams of water vapor per kilogram is a lot. All right, are we fine with this?
Yes.
Mm-hmm.
Okay. So what does Yoda always say that you have, what has to be true? There is no try,
Only do.
only do. So whenever we're doing these problems, you have got to do this. Now, I would have hoped, and I'm not sure from the other day, but did you go and actually do this virtual temperature correction? Nick, you said you worked it through. Jim, I know that you worked it through.
Yeah.
The only way you can do it is to actually go through it yourself.
Yeah.
Make sure that you realize you can do this. So there you go.
I sent you my proof whenever you're free to look at it.
Okay, wonderful. Okay, so I'm going to just open up a new, I'm going to open up a new file. New blank document. And now we're going to go back because we jumped ahead. The reason we jumped ahead is because it made sense with virtual temperature. So now we go to the hydrostatic. So turn to page 68. In your book. And figure 3.1. Now, the key here is to realize that we're in hydrostatic balance. Now, we've already gone through this. If you need to go back into a lecture in the past, I don't remember when it was, hopefully you do, but we talked about that slab, right?
Problem 3.1 or figure 3.1?
Figure 3.
Okay. There we go.
We said that the forces that are acting on it, right? There's a difference. There is you're basically saying there is a downward force, and here's the slab, right? There's the slab. So whatever that is, there's just a downward force. And what is the downward force?
Pressure.
It's pressure. And what's pressure defined as?
The weight of air above you.
So we have how much air is above me? Answer, above that slab, all of it that's above the slab. What is the pressure on top of the slab? It's a result of the weight above the slab. Below it, it's the weight below this, from below the slab. It's everything. So I'm also, not only do I have everything, I've got the weight of the slab itself. So the difference in pressure is the weight of the slab. Well, what is the weight of the slab itself? And this is super important that you think about how we're doing this, because there's going to be a problem that you need to do. What is the weight of this slab?
The pressure below minus the pressure above.
Well, no. I just want to figure, imagine that I just have this slab, and I want to know what the weight of that slab is.
Density times the area.
Well, yeah, because what is, let's just start simple. What is weight? Mass
Times gravity.
times gravity. Do I know what mass is? What is mass in this slab? Like, I'm trying to figure this. I don't know the mass of the slab, but what do I know?
You know its thickness.
You know the weight of the air above it.
Yeah, but
And
I
the
don't
weight
know
of
how
the
much is in the slab. What I know is, if I remember that density is mass over volume, then I know that mass must be density times volume. So the weight is actually density times volume times gravity. But what is volume equal to?
Area times delta.
Delta Z.
Right? Area times the delta Z. So this over here becomes mass times the area times the gravity. But do you understand how that's related to pressure? Because what's pressure given? What is pressure? Pressure is force over area.
Yeah.
But what's force? Mass times gravity over area. So if I take in this equation and I realize that I have gravity that I'd like to get rid of, and I've got area on the top, and I've got mass, then what I'm really saying is that the weight is related to the pressure of the slab. But it's not the pressure of the slab, it's the difference of the pressure of the slab. And that's where you finally get to this equation where you're saying delta P equals G times the density times the change in the height.
Negative, or are you putting that value?
Well, okay, so the idea is whenever you see negative signs, what do you have to kind of assume about this?
The force is going down.
And that's because you're going up, right? So what's the pressure doing as you go higher? The pressure is going down. And those are the kind of stupid things that can confuse people. So now they say on the bottom of page 68, they go, okay, well, now I can put it into these partials. Equals minus rho g. And in my opinion, I would say that this view of the hydrostatic or this version of the hydrostatic is the one that I usually teach. dPdz equals minus rho g. Now,
minus density times gravity then. Or negative density times gravity.
Negative density times gravity. They have gravity times density, but that's just the way I've always done it. Notice that they go on 318, they go to, instead of partials, they now switch it over to dPdz equals minus rho g. Now we know that for specific volume, we could also say it's going to be, they do this, they do dP over rho equals g dz, and they go 1 over rho is nothing more than alpha. So they go alpha dP equals minus g dz. Which is this version right there, this version here, that's just a trick that you're going to need to use. And you'll understand why in a little while.
Is there a reason why they the book tends to change that to alpha a lot of the time, where they do 1 over the?
Okay, so let's see if we can theoretically explain why that's the case. Before I do that, Nick, I just want to have you read the little note on the bottom of page 68. Because the variation of pressure with height is taken with other independent variables held constant. So I'm gonna just, you don't have to write this down per se. All we're saying is that the change in pressure with height, if I look at what a total derivative is we would talk about expanding those other terms where we have this.
Mm-hmm.
Right? We have those other terms.
Yeah.
And there's things that you'd multiply by and all this other stuff. But we're saying this goes away. So we're saying I can go this way because, and here's the key, I am not supposed to manipulate this. When I see a partial derivative, I'm not supposed to rip it apart. That's supposed to be illegal. I can do that with this derivative. I can do that with total derivatives. So this, ripping it apart is illegal. I really shouldn't be integrating with this. I should be integrating with this, supposedly. And again, this is not super clear to me. I just know mathematicians go, you can't do that. And I'm like, okay, whatever. I can do this, though. And that's why we get to this thing.
Okay.
Okay, so now, does that make sense to you? I don't know if you've ever seen that, but I know that when I was learning it, I was like, what? And that's why that little note in the book says, you know what? We're going from the bottom of page 68 on the left side to the right side, and we're going to derivatives now that we recognize, and now I can rip them apart.
Okay, yeah, that makes sense. I still don't get why they substitute the alpha in, though, for 1 over density.
Okay, so what you have to recognize is this. I have dp dz equals minus rho g.
Mm-hmm.
If I went this way, and I said, let's integrate. See, because now I'm taking that slab, and in derivative form, how thick is the slab?
dz.
dz, it's infinitely thick, infinitesimally small thickness. But what's the change in pressure?
Would have to be, well, if we consider it's infinitely thin, would there be?
Wouldn't the pressure change be infinitely small as well?
Yeah.
So I'm saying I'm going to go from the surface pressure to 0. I'm going to integrate this. Can I integrate that? Piece of cake.
Yeah.
Right? That just becomes P integrated from 0 to P naught, which becomes minus P naught, which the minus signs go away. We're all happy with that.
Yeah.
Okay? So I just wanted to show you that's what I could do. Can I integrate this side? And that's the worst integral sign ever. Can I integrate this side?
Yes.
Ha.
Pull out the constants.
Okay, so you fall for the this absolutely wrong thing. I caught you dead in the tracks. I can't bring these two out. Why not?
Because they rely on the level that you're at.
These,
Yeah.
Oh, they're
are a
dependent.
function of height.
They're
Yep.
dependent on Z.
Dependent on the height.
Mm-hmm.
So I can't do that. So if I keep density, so before I do all this integration, let me just erase all this stuff. What I'd want to do is I want to bring the pressure, the density on the other side.
Okay.
So by bringing it over here, and this side stays as just G dz, I realize that this side is 1 over rho. It's just easier to write alpha. Because remember, alpha is 1 over rho.
Okay, so they're just doing it as a substitution because they just want to.
It's a notation thing.
Yeah. Okay. I wondered if there's anything special to it, but I guess
There is
not.
something also very special that we're going to get into when we get to the first law. Okay? If I took a box of air and I said, I heat the gas, but I keep it as a true box, a rigid box. Do you understand the box is a volume, and what the pressure is going to be doing is changing? If I keep it in this box, then I can look at this and keep the volume constant. If I heat the gas and it expands, then the volume's changing, and I got to know that volume is dependent on pressure, and I can't integrate that. But I also want you to understand, we'll see that when there's an expansion, there's going to be a work term, and this will be what the work is.
Okay.
And you will also see the G alpha. So when we get to the first law, I want you to be aware that you're going to see these a lot. Well, if I ever, but the point is, if I ever see alpha dp, that becomes very simple to say I can substitute that with G dz. Now, this actually goes to the next thing. Can I integrate this?
Oh.
If you know the equation for the gravitational constant.
Well, is gravity constant with height, or is it dependent on height?
Depends on height.
It varies with height.
Okay, so if it depends on height, then I can't do that. Now, some of you are sitting there going, what? What do you mean gravity depends on height? What is gravity on the Earth defined as?
I believe it's the pull of the Earth.
And where's the gravity? Everything's based on the center of gravity,
which is the center of the planet.
So when I'm on the surface of the Earth, I actually have a distance. What is the distance from the center of gravity to the surface of the planet?
The radius?
Radius of the Earth.
Right, 6.37 times 10 to the 6th meters. Right, that's the radius of the Earth. If I go higher, if I go higher, do you understand now I'm a further distance away? Do you remember gravity is proportional to 1 over the radius squared? It's called the inverse square law. Are you aware of that?
Yeah.
You need to know this. The inverse square law. So the fact that I'm going higher up, I'm actually losing, I have less gravity affecting me because I'm further from the Earth. Now, look at page 69. And they give you table 3.1. And what you see is, okay, at 1 kilometer, you have gravity, which is 9.80 as opposed to 9.81. So it's changed by a little bit. At 10 kilometers, it's down to 9.77. Now, you could say, well, that seems pretty constant. Let's just ignore that. If you go up to 500 kilometers, 8.43 is considerably different, right? That's not something that you could ignore. So you're really ignoring gravity a lot of times in the lowest 10 clicks, and that would be okay. But if you're shooting a rocket to space, dude, you're not going to win. You're not going to shoot that rocket ignoring the fact that gravity changes.
Is that sort of like how if you like shoot something into water, the first few inches it'll be fine, but the further you go, the more it just diverts?
What?
Is it sort of similar in concept to that? Like how
What are you shooting into water?
what?
What are you shooting into water?
Just anything. Like if you like fire an arrow into water, like the first few inches it'll go fine, but the further it goes into water, the more that it gets pushed around or moved.
Well, things, you shoot a bullet in the water, the bullet will disintegrate and stop within a couple of feet. Somebody shooting at you, jump in a lake.
Yep.
Don't make it through water.
I
Especially
remember that Mythbusters episode.
that was a cool episode. That's what you're talking about. That has nothing to do with gravity.
I was asking if it was a similar concept or if it's a completely different one altogether.
I think it's completely different altogether.
Because the
Alright.
density of water is too much so that it ends up stopping the bullet compared to air.
Yeah, the density is way too much. It's way tons of friction and resistance, and it's moving it so fast. You know, things slow down when they hit terminal, or like if you shoot something faster than terminal velocity. Here, you know how people say, well, what if you dropped a penny from the Sears Tower? Would you kill someone?
Yes.
And the answer is no. A penny will not, because the penny can't go faster than terminal velocity, and the terminal velocity of a penny is pretty slow. In fact, if I whipped a penny at you, I believe that I would actually start slowing down. Now, I'm not going to throw a penny through your skull. I'm not that strong. And if it's slower than that, then the penny will be resisted by air. A big rock will kill you because its terminal velocity is much faster. But that whole idea of killing somebody with a penny is nothing. It's going to float most of the way down.
Hey, Paul, have you seen X-Men First Class?
I've seen it. Which part?
The part where Magneto takes the coin, puts it right through the guy's skull.
Well, yeah. Well, he's got some superhuman things where he can move
Yeah,
things.
that's besides physics, but
Okay,
what it reminded
so
me of.
basically what we have now is we're going to define something called geopotential. So on the bottom of 68, now we're in section 3.2.1. The geopotential, so look at the definition. It's the amount of work done against gravity to lift 1 kilogram of mass from sea level to that point. And they're going to use phi. Because it's work, right? It takes work to lift air because you're fighting against gravity. Remember, it's force over distance. So it's going to be joules per kilogram. But a joule per kilogram, just like CAPE, is actually meter squared per second squared, just like helicity or shear. The force, it says, acting on 1 kilogram at height z above sea level is numerically equal to g. The work in joules is z to z plus delta z, or dz, is g dz. So then they go, I'm defining this, and this is kind of a weird, thing. We're saying the change in the geopotential, capital phi, is defined as g dz. But we know that g dz is also equal to minus alpha dp. So that equation there on the bottom of the page, 320, or 3.20, is really big. But because this is a derivative, and the reason we do a derivative, and this is so bizarre from a calculus standpoint. So imagine that we've got our slab, and we said, how thick is the slab? And we go dz. Or we say there's a change in pressure of the slab, dp. How thick is that change in height?
Infinitely small.
Infinitely small. If it's infinitely small, we can assign gravity at that point because it's infinitely small. So there is a value of gravity right there.
So are you talking
We're
about
not worried about the change in the gravity. We're saying here's the value the gravity is as you're at that place.
So that would be considered the local derivative then, and then what we're doing for this d phi is the global derivative. Is that why?
Yeah, but we're not, we don't really want to think of, we don't have to deal with this in terms of total derivatives. We're not looking at temperature or time changes. We're not looking at effective terms. We don't care. So we're just saying, I don't care how we call it. It's a derivative. And that's what happens in science. We get imprecise and sloppy because we don't care. And that's what the bottom of that page says, really far bottom. So if I'm going to take this, I need to integrate this equation. And I could also integrate this equation. So I could integrate all of this stuff. Does that make sense to you? Now, when I integrate just the derivative, you understand I'm getting just this. Technically, it's from, what is the work done to lift a parcel? Obviously, if I'm at the ground, there's no work that's required, so it's always from 0 to the geopotential. That's why. And that becomes this minus that. I hope you understand what I'm talking about.
Is it 0 to phi or 0 to z to some height?
Well, it's the geopotential. No, because geopotential is defined as the work required to get some height.
Oh, I see.
So you think, what's the value of that geopotential? Okay. So regardless, you're saying, okay, now geopotential at some height, that's where they do. And then what we're going to say is we're going to go from 0 to that height, and then we'd have to go g dz. Then they say, I'm going to do something even crazier. And I'm going to say, I'm going to define something, capital Z, which is now geopotential height. And we're going to define it as the geopotential at some height divided by gravity at the surface. But if that's the case, I need to do this. Realizing, number one, capital Z is not little z. Number two, I don't know what this is. But if I'm calling it geopotential height, I don't care what that is because I'm just going to define this term. So it says right after equation 3.22, take a look. It says G naught is the globally average acceleration at the gravity of the Earth's surface, taken as 9.81 meters per second squared, or meters per second per second. Geopotential height is used in vertical coordinate in most atmospheric applications. And you look at the table, now that table also gives you geopotential height. Notice it doesn't change much in the troposphere. From actual, so the actual height versus the geopotential height. If you go up higher, it's a lot different. All right,
What's
now,
the connotation for the thing under 1 over, and the last thing you wrote, gosh, I wish I could point.
What?
When you have a geopotential height equals phi z over, what's that symbol? GO?
G naught.
G naught.
G naught. Okay, okay.
That's that right there. That's 9.81. So you've never probably paid attention to this, but when I go to the models, and let's just go to the NAM, and I'll go to 500 millibars. Over here, I say, oh, this is 5,880 meters. We said that's the height. What is this really? It's the geopotential height. So our models are actually dealing with geopotential height, capital Z, not little z. So in the hypsometric equation, we want to do that. And basically what we're saying is that the geopotential height doesn't deal with the fact that gravity is changing. If I'm using geopotential height, I don't need to do the integration, and I just need to use 9.81. Realizing that if I want the actual height, that's a problem. Now, if I'm launching a rocket into space, I want to know its actual height for altitude. And the higher up we go, the greater that difference is. Now, it says, the next paragraph, in meteorological practice, it's not convenient to deal with density of a gas, the value of which is generally not measured, right? Bob doesn't tell you density. Bob tells you pressure, temperature, and dew point. Now, could you calculate, here, let's do this. Let me go back here, go back to my screen. Oh, I didn't need to take a picture. Can I calculate the density of air at a height?
Yes.
It would become, is it possible to do that? And the answer is, well, it's possible, because if I use the ideal gas law,
Bernard.
but I can't do that, can I? Would I use this one to calculate the density?
No.
What would I use?
The one with dry.
And so I would have to do the virtual temperature using the dry gas constant. And the virtual temperature, I would need to know W. And Bob doesn't give me W. I need to know the dew point, which will tell me W. Then I use the virtual temperature correction as an approximation. And then knowing the pressure and the virtual temperature and the ideal gas constant, I now could solve for the density. So it's possible. It's just not very convenient. There's a lot of steps that I would have to do in order to calculate that, because I can't just use temperature, because I can't use the ideal gas constant for dry air. I'd have to know how much percentage of it is water vapor. So what we're going to do here is, it says, by making use of 3.2, and what do you think 3.2 is? The ideal gas constant. So we know, look over here, we know this. I know density is pressure over RD TV. So I plug that in here. Okay, so now watch, this is fun. And when I say fun, I'm kind of a masochist. Okay, so I'm just going to erase all this stuff, keep everything else in place. I'm going to say, all right, dP over dZ equals, substituting in for density, P times G over RD TV, and I need a minus sign in there. Now I do this. Okay? Why do I want to do something like this? What's the purpose of doing that?
To do the integral.
Because when I integrate that, I get what?
Pressure.
No. When I integrate dP over P, what do I get?
LNP,
You get the natural log of P.
natural log.
This, my friends, is a simple way to integrate. I can do that. That's easy. If I integrate this side, can I do that?
No.
No, because G is dependent on Z.
Okay, but instead of doing that, what I could just use is, instead of this, couldn't I just go, oops, that's terrible, d phi? Isn't that the same thing? Didn't we define it that? So that's really negative d phi
Yeah.
for RDTV? What's this?
The dry air constant.
So if I integrated both sides, let's go back to red. I integrate this side, and I integrate this side. Get rid of this minus sign. I can integrate this. I can bring this out front. So I can go equals minus 1 over RD. And I'm integrating d phi, but I have TV. Can I integrate it with TV in there?
No,
Why not?
because it depends on where you're at.
This is geopotential, right? This is geopotential height. You can think of geopotential height, you can think of geopotential. It's a vertical most place in the atmosphere. And do you agree that the temperature, the virtual temperature, changes with vertical height?
Yeah.
So I can't integrate this. But what if I said, well, gosh, let's, instead of doing this, let's make it an average temperature.
Okay.
If it's average, do I care about the variations within it? If I said, what's the average?
No.
Then I can bring it out. So if I use minus 1 over RD over that, now I have d phi. And on this side, I have dp over p. And I can integrate it. And that's really simple. So if you look on top of page 69 on the right side, this is what they're saying. The only difference here is so take a look at top of page 69 on the right side. They separated out the geopotential. And everything else is the same in there. They switched negative signs. Figure it out. Then you integrate easy. You're the difference in geopotential. Yeah, and the RD comes out, and then I've got this thing. If I divide both sides by gravity, G naught, instead of geopotential, I have Z, geopotential height. And it says the difference is referred to as the geopotential thickness of a layer. So this equation, now I'm going to delete all of this. This equation, 3.24, can be written as this.
Oh.
If I know the average temperature of that layer.
Virtual temperature.
Average virtual, technically, virtual temperature. Do you have my old severe weather glossary? I think that's a glossary you should have. You guys have that one?
No.
Okay,
I've got
let me.
it somewhere in my old notes stash, but it's not easily accessible at the moment.
Well, it is. Remember, it's in academics. Severe and unusual weather. Here's the glossary. You can always grab it there.
Oh.
And if
Forgot
I
about
look at hypsometric, look what it says. An equation relating the vertical distance between two isobaric surfaces to the layer's mean virtual temperature. In all my other classes, we just said the average temperature, the average temperature. But really, it's the average virtual temperature. So it was in there. And since the isobaric surfaces tend to be known, like 500 millibars, you're looking at the geopotential height of 500 millibars. You are looking at the change in the geopotential. So when we get here, let's integrate. So this side is going to be delta capital Z, which we said is the thickness between isobaric layers, is equal to RD, mean virtual temperature, over G naught, times the natural log of P integrated from, and in this case, I can go from P1 to P2. Okay? So this is from P1 to P2. Keeping in mind that when you integrate natural log of P2 minus the natural log of P1, that is equal to the natural log of P2 over P1. Remember that rule of logs?
Yes.
Just a reminder, right? I'm just kind of reminding. But the value of P1 is going to be what compared to P2? If I'm going from Z1 to Z2.
Less.
Right?
P1's going to be greater than P2.
So you can get negative signs in there, but if I have a negative sign, what can I do? I can flip them around.
Right. Okay, hold on. You have a negative sign, you can flip them around.
Like if the value of this becomes negative, anytime you have a negative value in here, that's like putting the negative value outside.
Oh, I see what you're saying. Okay. I see. Yeah.
I like it. If I did this, that's the same thing as the natural log of P1 over P2. So if I put a negative sign, I can flip it here. Just keep that in mind. That's all I'm saying. Keep that in mind. That I can do stuff like that if I wanted to. Whoa, that was one too many. There we go. So when I get to here, I'm like, okay, this is fine. So what I'm really saying is that this equals RD over G naught times the mean virtual temperature times the natural log of P2 over P1.
And wait, what happened to TV there? Did we pull that down, or is it supposed to be on the...
It's here. It's right here.
I mean, is it still...
It's the same. It means the same thing, James.
Oh.
So in other words, I needed to have a constant. Meaning, if I know the average temperature of a layer. Now, by the way, look over here. Look, turn page 70. And we'll go into this in more detail, but look at figure 3.2. They're taking a layer of the atmosphere, and they're calculating from the radiosonde what the approximate average temperature is. And in order to do that, we need to plot it out versus the logarithm of the pressure, because it's not, the axis would be exponential. We don't want that. We want linear. And then they just do these little equal areas to make these little triangles on that sounding. So in other words, look on the screen. I have a layer of the atmosphere. And we're trying to say is if I can determine someplace in here a point where if I created little triangles and a little triangle here, I have equal area. And so that point is your mean virtual temperature. But again, you'd have to plot virtual temperature with a logarithmic p to do this. But if once I assign it, and now I'm going to make things a lot simpler here, so watch this. Imagine that the lapse rate of the environment were just a line. It's a lot easier to estimate that this is the mean virtual temperature. And you could take a different one and you could say, well, that's a steeper lapse rate, but the mean virtual temperature hasn't changed. So if I can figure out the mean virtual temperature, this becomes a constant. Even though it's changing. That's why we say it's proportional to the average virtual temperature of a layer. Because you got to know that. Now, RD over G naught, those are both constants. So what do they call this in the book then? This is a number, right? What's the value of the number? What's RD over G naught? Calculate it. What's the value of RD? And don't worry about 287, right?
Yeah.
And what's the value of G naught?
9.81.
So do 287 divided by 9.81. What do you get?
29.26.
Okay, rounding it, 29.3. Look at equation 327. 29.3.
29.3.
But when you multiply by the average temperature, then you are now defining this side to be H. So this whole thing is H, which is the scale height. And why is that? And what they did, now look over here, look at equation 3.25. They said that the change in the height, delta Z, Z2 minus Z1, is equal to H times the natural log of P1 over P2. And what we do in that is in order to take this, so let me go.
Oh, they're going to exponent. Okay.
Let me go over here, right? They're going Z2 minus Z1, capital Z, is equal to H, this stuff, times, it's just ugly, H, times the natural log of P2 over P1. But I'm taking both sides to the exponent. I'm taking e to both sides. And when you do that, oftentimes they won't do that. They will say the exponent of Z2 minus Z1 equals the exponent of H times the natural log of P2 over P1.
Yeah, okay.
And what I know, actually, you know what, I kind of made a mistake. What did they do first? Before they took the exponent of both sides, they divided both sides by H. So really, the H doesn't go here, the H goes here.
And
so
bring parents down.
You have the exponents.
Right.
There, right? Do you see what that's going on in 320?
Right.
And the exponent of natural log is nothing more than P2 over P1. times the exponent of Z2 minus Z1 all over H. And then they bring P1 over to the other side. Exponent, sorry, Z2 minus Z1 all over H is equal to P2. Now that is what they have. And if you remember, we said if we change height by a scale height, that's an exponential drop in pressure. So if we say this is -1, you're saying that the height that you're changing is one scale height to drop by a factor of E.
Right.
So that goes back to this concept of scale height, which is why in this hypsometric equation, we can use H, which is scale height. Notice in 3.2.2 section, what do they say the temperature was in this example?
255 Kelvin.
Well, no, I mean, what do they say right in that first paragraph? They say for an isothermal, they're saying, okay, so let's not worry that temperature is changing. Let's just say call it constant.
Constant.
Go to the next page, and then they talk all the way down to equation 3.29. And they go Z2 minus Z1 equals, and here they're using H prime. And what they really mean is RD over G naught times the average virtual temperature, or you could have said 29.3 times the average virtual temperature. Those are all equivalent. Times the natural log of the ratios P1 to P2.
The ratios are inverted.
The natural log part is.
That's because of the minus sign.
Figured it out.
Yeah, right.
If you have a minus sign, it goes away.
Yeah, there's the trick.
Those are the stupid tricks that you sometimes go over. Where did it go? The minus. If I put a minus sign in there, the pressures would flip. You understand? If I put in minus natural log of P1 over P2, that's like saying I can go natural log of P1 over P2 to the -1, but that's like saying the natural log of P2 over P1. But see how these things are the same?
Yeah, that wasn't the question I had. I kind of resolved it. I just realized I looked at something wrong.
Okay. So that's called the hypsometric. So this equation here is your best way of defining what the hypsometric equation is. (29.3) is the value of RD over G naught.
Oh, duh.
So if I look at a sounding, you remember how we did in the worksheet that we did, you have a sounding, and I said, find the scale height. And you said, okay, the scale height is just where the pressure drops by a factor of E.
Right.
Right, and you go, oh, on that sounding, here's the height. Well, boom. If you know what that is, then you know what H is. And if you know what H is, you know that H is RdG naught times the average virtual temperature. So if I know the scale height, I know the virtual temperature of that average virtual temperature of that layer, because I can plug it in and solve for it. So I'm looking at soundings to figure where does the pressure drop by a factor of E from the surface pressure. And then I know what the average virtual temperature would be. So in exercise 3.3, they say calculate the geopotential height when the pressure at the sea level is 1,014, and you're looking at the geopotential height of 1,000 millibars. Well, they go, the difference in that is just going to be H times the natural log of P naught over P, or over 1,000. And they go, okay, it's a scale height. And now, how did they go 1 plus that? What did they do? And what they did here is a stupid cheat. And again, I'm not a big fan of cheats like this. They said the natural log of 1 plus x is approximately equal to x if x is much less than 1. See, I don't know if you remember in class, you have the double less than side, means much less than. So if x is really small, a lot less than 1, this is like a little thing. It's a cheat, just like we did the cheats in the other thing. Earlier today, we did some cheats. And then what that ends up becoming is approximately 8 times the difference in the pressure. And why 8?
So X is around 8 in this case? Or when you...
Because H is approximately equal to 8,000.
Right?
So they're dividing 8,000 by 8. They're pulling out the 1,000 denominator.
Right, and this is why you get this concept here, which is kind of fun. Pressure drops by 1 millibar in 8 meters. So if the pressure dropped by 14 times 8 is 112 meters. So when you're down close to the ground, this is only down close to the ground, pressure is dropping by about a millibar every 8 meters. So you're going up in an elevator up a very tall building, your pressure is dropping by several millibars in the building. And that's why, and your ears can't adjust that quickly. That's why your ears pop. I don't know what your ears can adjust to pretty quickly, but in an elevator like in the Sears Tower, your ears are going to pop.
When you say at low altitude, what's the limit on that?
Somewhere around 1,000 millibars or lower.
Okay.
Or just above that. So this problem is just a trick they did. And so what that leaves us here is to go to page, on page 70 and all this high mathematics. And I'm going to kind of skip over that. I'm not that worried, but I want to point out something which is important. And that's equation 3.28. And you will find this in a lot of calculus books and a lot of calculus classes you take. This is a way of doing averages. And the reason you're doing that is if you look up there you're doing an integration of the virtual temperature times the change in pressure, which is going to be summing up the area. So that's the area in the diagram. CDE is equal to ABC. And when that's equal area, then the point that you're at is going to be your mean. When you do mean value theorems in calc, and you'll see these in your, Nick, do you remember some of these? Allison, I don't know if you taken it.
I remember.
That's going to be an equation like this. So I'm not going to go through that because I don't care. Now, going back to this. Let me get rid of this. Going back to this equation. What if I'm doing 1,000 to 500 millibar thickness? Then what does this become? This becomes 29.3 times the average virtual temperature times the natural log of 2, right? 1,000 to 500 millibars. What's the natural log of 2?
.69.
My back.
Multiply 0.69 times 29.3. What do you get? What's the answer? Somebody tell me.
20.2.
Okay, so we must have done some rounding in there. But if I say 20.3 times the mean virtual temperature, and the answer is in meters, that's the thickness. 1,500 millibar thickness of this. Okay, do you remember the rain snow line? By the way, I'm looking at the bottom of page 71, left-hand side. What's the rain snow line? You remember what it is, Jacob? Of course you do. Jake?
Not off the top of my head, no.
Oh, rain snow line. Anybody?
No.
Critical thickness. Rain snow line is 5,400 meters. So that's what delta Z is. So what's 5,400 divided by 20.3? You guys have-
266.
How much?
266.
Now, do you agree that's pretty cold? And the colder we are, the less the virtual temperature correction. Right? Because look, remember the virtual temperature correction was the temperature times 1 plus 0.61 W. So the ratio of the virtual temperature to the temperature is equal to 1 plus 0.61 W. Well, when the temperature gets smaller, then we're not going to have a lot of water vapor. If this becomes smaller, then the value of these two become closer and closer to 1. So there's a smaller difference when the temperatures are cold because I don't have any water vapor in the air. So this is a lot closer to the average temperature. And so we're looking at an average temperature that's fairly cold. Now, under what conditions would you expect there not to be snow, even if you have thicknesses below 5,400? So let's say I have a thickness of 5,400 meters. And I'm saying, is there going to be snow today? Under what condition would you think there would not be snow?
If there's no clouds in the sky, for one.
Well, no. I'm assuming there's precipitation.
Sorry, I didn't
your
quite
virtual-
catch that one. Connection's cutting out.
Jim, what did you say?
Virtual,
My connection's
the
really-
ratio would be small? TV over T, is that what you're getting?
You're here. You guys are missing the idea,
Okay.
and that's okay that you're missing the idea, because this is not something that I think is simple. So I'm going to go to the models just for a second. I go to the GFS. If you look under here, under precipitation products, you will see that we do in here a precipitation type, but we also do critical thickness. And the critical thickness lines are up here. And the critical thickness that I care about first, as a first approximation, is down here. It's the white, 1,000 to 500 millibar thickness of 5,400 meters. So if I look, here, I can get rid of this. If I look over here and say, here is my white line. I'm saying that any precipitation to the north of that white line would be snow. That's a first guess. And anything to the south of it would be rain. That's how you use those critical thickness lines. Okay, so before I do that, let me go a little bit further and see if I can find a better example. Because I really want to find one where it is going to snow someplace.
Excuse me.
And it's not a whole lot of anything. But how do I know, what are these other things on here? What are the colors? Well, the colors are relative humidities. So I'm going to assume that when I'm up in the 90% relative humidity or above 95%, which is where I get blue, that's when I'm expecting precipitation. So I'm over here. This area up here, 291 hours, is well north of the 5,400 line. I'm expecting snow. I'm saying that the average virtual temperature is cold enough to support a layer that should be snowing. So if I think of a sounding, and my sounding looks something like this, and the average of that layer was 266 or less than, right? Then that gives me a thickness of 5,400 meters, and I would expect there to be snow. But of course, what are we assuming is true? Do we assume that the snow starts up here someplace, right? It starts as snow, and then even though the temperatures start to come up, right, we're assuming that at some point it's going to stay cold enough to stay as all snow. So even though it may get warmer down here, it's still staying as snow. So under what conditions would I expect it to melt down here and come down as rain? What would the temperature have to be down here?
Warmer?
Huh? It would have to be warmer, right?
Warm.
But if I made the temperature warmer down here, then what would that do to my mean virtual temperature?
Increase it.
But I don't want it to increase. I still want it to be lower than 266. So I would have to be colder higher up.
Oh, I see what you're saying.
But what have I done to the lapse rate in that scenario?
Made it like super steep.
Right? I've
Almost
gone
adiabatic.
from this lapse rate to this lapse rate, so I've increased the lapse rate. But a greater lapse rate is telling me that the air is more unstable. So if I get more unstable and I still have a lapse rate of 266, I mean a virtual temperature of 266, but the air is more unstable, that's much more likely that the snow will become rain. That's why this is a first guess. This is not a true statement. We're
First
guessing.
approximation.
Because what happens is, when will that not be true? When will it not be snow if the air is too unstable? So in other words, I might have a situation where I've got convective precipitation that's cold, but I'm going to get a shower that forms and it will stay as rain, even though it's very cold aloft. So this is how you start thinking of these critical thickness lines based on lapse rates. I hope that made sense to you.
Yeah.
I think I have to rewatch it because my internet dropped for like a good 10 minutes there.
Well, okay, it's all on here, so rewatch it. But there's some cool stuff in this. But that's how we use these critical thickness. Now, in this case, it seems pretty obvious that up in Canada, this stuff is going to be snow. So if I go here to precipitation products at 291 hours, let me lock that in here. I do have some precipitation up there, and if I go to precip type, I don't know why they're saying it's rain. Oh, that's reflectivity. No, it is. Why is it not snow? Look at the sounding. We always wait for climate. Oh, okay, and we see here, why is it rain? Well, our temperatures up here are, there's your freezing line. They're well above freezing with high dew points. So, I mean, the dew point's still 40, which means your virtual temperature is going to be slightly warmer from 1,000 to 500 millibars, and you only drop to this temperature. So if I were to say, there's my basic line, my mean virtual temperature is going to be somewhere around, I'd have to do log, but maybe somewhere around here. That's around -8. 273 minus 8 is 265. So we're right on the border of rain snow. It's probably not going to work because these are fairly steep lapse rates. So it's possible it would be rain, possible it would be snow. But that's how these things play themselves out. Okay, now for next Tuesday, what are we doing? I want you to study up the page 71, super intense. And I want you to draw a cold core low and a warm core low using isobaric surfaces. And I want you to draw a warm core high and a cold core high. So similar to this, but try to be a little bit more precise. Then page 72, take a look at that. 72 is some information. You should be able to figure this out, but this is how we set altimeters. So Mike, when you're watching this stuff here is about how your altimeters are set. And I know you've got some air density issues based on this type of stuff. Then the next stuff is the first law of thermodynamics. So I want you to read pages 72 through 79 and take notes on and study it up. And also watch that mechanical universe on the first law of thermodynamics. And that is your assignment. And that
Is that?
class. Where are you guys?
Which video is the one on thermodynamics? Is that
It says the first law of thermodynamics in it. Oh.
All right. Once the video's up, I will rewatch what I missed and all that fun stuff.
Okay, where do I stop? Oh, here we go. Stop share. And oops, you guys popped over there again. And then record.